global competitiveness of the UK maritime industry through extensive partnerships and innovation projects. It gives me great honor to introduce this first talk today around the topic of powering the future with fuel cells in the maritime shipping. We have two brilliant speakers. First of all, we have Nicholas Abson. He is an international fuel cell expert with over 30 years of experience shaping the future of transformative technology. And working in this area since the early 1990s, Nicholas has specialized in the development of innovative fuel cell technologies, earning a reputation as a pioneer in the field. We then have Isabela, who is a visionary leader in the maritime and energy sectors with over 25 years of experience driving transformational change and is co-founder of Clean Maritime Shipping, a pioneering tech startup specializing in hydrogen fuel cell technologies that utilizes waste as its primary source. So we're in good hands with our two speakers today. Yeah, without further ado, I'll hand over to Isabela, who's going to give a bit of an introduction around the purpose of the webinar today and spell out those details. Over to you. Thank you both.
Thank you so much, Jake, and thank you so much to MarRI-UK for organizing this series. And welcome, everyone. I'm so excited to have the opportunity to discuss a topic that I'm truly passionate about, together with my partner and mentor, Nicholas Abson. I would like to give you a quick agenda of today. We start in approximately 5 minutes with Nicholas that will give us a guide through the history of fuel cell and their use. He will cover the origin of the technology and its evolution. Then he will move into how the technology works. We'll break through the basic of fuel cell and the types used in maritime application. Then at 15:40, I will lead the maritime application section where I will outline the economic and operational impact of integrating the hydrogen fuel cell in shipping. And we'll finish at 15:50 with questions that gives the opportunity to interact directly. And then a wrap-up session. The key objective is to provide a comprehensive view of hydrogen fuel cell and the transformative role in maritime operation. Our key objectives today are to understand the fundamental of hydrogen fuel cell, how they originated, how they work, and why they are essential for the future of marine shipping. And second, to explore the economic implication and market potential, illustrating how adopting this technology can be both environmental and economically beneficial. So we ultimately want to foster a collaboration between all the stakeholders in the maritime sector. So thank you again for joining us and look forward to interact. So who we are. As a founder of Clean Marine Shipping, I like to share a little bit about our mission. Our startup is dedicated to bringing sustainable, innovative solutions to the maritime industry. We specialize in hydrogen fuel cell technology, particularly using waste as a primary energy source. Our work involves developing cleaner energy systems for marine systems and port operations. And our mission is to drive changes in maritime operations. We really believe that together with the partners in the industry, we can really do some changes, huge transformation. Next slide, please, Ola. So therefore, I'm going to pass you now to my partner in crime, Mr. Nicholas Abson. As Jake mentioned, he has been working in the field for the last 13 years, and I'm so proud to say he's my mentor and my partner in crime. Over to you, Nick.
Right, good afternoon. Well, I'll give you a brief bit of background of my past and my involvement in fuel cells. I I was a television director for 20 years, which has nothing to do with fuel cells at all. But I did make science programs. In fact, I made most of the science programs for the independent television networks. I'm neither a scientist nor an engineer. So all of the things that I do within fuel cells came from point of view of total innocence. I say that because I had to learn everything. And that was rather a good thing because it meant that I came to it clean. The invention of fuel cells, next slide, please. Hello, next slide. Yeah. Fuel cells were originally invented in the 1800s by William Grove. We'll go a little into what he did. He was, in fact, actually he was a reverend. He was a religious man. And he built a fuel cell that actually worked on coal, would you believe? But for the fuel cells that we know and understand now, we have to go to the space age. The first fuel cells were used in space, or to be more correct, in the originally Gemini, and then the Apollo project. So it was actually the driving force behind fuel cells was the use of them in space. And they were used primarily because battery technology at that time was not sufficient to be able to provide sufficient amount of power in small enough space to be able to meet the needs of the space programs of the time. Nowadays, in fact, they do use batteries, but that's because battery technology has moved very rapidly and very well. So next slide, please. So I call this Who Do We Blame? Because I feel a bit like a victim when it comes to fuel cells, because I didn't start out by wanting to do fuel cells. I started out by wanting to report on fuel cells for a television program. Unfortunately, the company that I was highlighting in the television series was a Belgian company that went out of business. So I ended up actually buying it, which was a mistake because it has turned my life around completely from being a television director and being lauded to being a fuel cell guy and being forgotten. Anyway, William Grove, I've just gone over a bit with you. He created an acid-based fuel cell using sulfuric acid and hydrochloric acid. And it was very clever because, of course, it hadn't happened before. And he used coal gas to power it. So it didn't have a very long lifetime, but it did work. The most important change was when Tom Bacon at Cambridge University came along in the late 1930s, and through the 1930s and 40s, continued to develop fuel cells at Cambridge University. It's a misnomer that Cambridge University actually was the driving force behind the fuel cell. In fact, the driving force behind the fuel cell originally was a company called Marshall's, which did maintenance on aircraft engines. And old Mr. Marshall funded Tom and his work until the Apollo space program came along. He built a very clever fuel cell because it had 1 amp per square centimeter, but it was extremely expensive, using very large amounts of platinum and very large amounts of gold as catalysts. But it worked, and it worked very well. And so it was taken over to America, and NASA continued to help develop it along with various US companies who were involved in the application of fuel cells at the time. So we've got Tom Bacon to blame. Then came Pat Grimes. Pat Grimes is less well known, but Pat built the Allison tractor. This was the first really practical use of fuel cells in transport. And Allison was the company that made the tractor, but it also made the fuel cells. And it would have been a success for one, but for one problem. And that problem was it was taken around to county fairs in the US, and it was panned by the farmers. And the reason being is it didn't make any noise, and therefore the birds weren't scared off from eating the seeds on cedars. Then we come to Karl Kordesh, a rather lovely man from Graz University. He was running all the science at another American corporation. This time he used fuel cells produced by them on a DAF variomatic. No, sorry, not a DAF variomatic, an Austin A40, and drove from Chicago to New York on it, which at that time is probably still quite a feat, as people don't tend to use them for long range. Then we're going to come back to the UK and Keith Williams. Keith Williams was a rather enigmatic character. He was the director of Thornton Heath Laboratories for Shell Oil, and he built a fuel cell car, being a DAF. Anybody trying to remember a DAF from those days will remember it was called the rubber band car because it had a rubber band, basically a rubber band transmission. Anyway, he made it go very fast, very quickly, and did 0 to 60 in 3 seconds. So that was quite a feat. But he used as a fuel, he used hydrazine, and there's a wonderful photograph which I don't have and which I did of Keith Williams pouring hydrazine into the car petrol tank while smoking a cigarette. Anybody who knows anything about hydrazine is highly explosive, carcinogenic, but an extremely good fuel. Then came General Electric, or around the same time, the phosphoric acid fuel cell was produced, and eventually was manufactured by United Technologies in Connecticut. And the first big use was with the Duke Power Company, and a US utility, who used it to produce power locally, but it wasn't terribly successful. It did last for a couple of years, but with an awful lot of maintenance. And that was one of the big problems with phosphoric acid fuel cells, that they did require a serious amount of maintenance. Then, or around the same time, most of these developments happened around the same time in the mid-60s and early 70s. So we had Westinghouse Electric Company produce the solid oxide fuel cell. And I'll go into that more about that later in the explanation of what they're like and what they do. But it was a breakthrough, and it was a breakthrough because it was neither acid nor alkaline. It wasn't neutral either. It sort of flops between the two. Then there is Walter Grott. Walter invented Nafion when he worked for DuPont, and in those days it was called DuPont Numiers, and he is still around actually, and his son runs a company that produces Nafion. Then my friend Jeff Ballard, who started the Ballard Fuel Cell Company in Vancouver. Jeff was a rather feisty but very entertaining man. But he wasn't one of these people who would go around and say how wonderful he was or how wonderful everything was and how wonderful the Ballard fuel cell, the PEM cell was. He, in fact, was a rather dour character. And he did not believe that PEMs would be the automotive answer to the internal combustion engine. A lot of people thought he did, but he didn't. He was quite sanguine about it. He left Ballard when the share price hit its peak of $168 a share, I believe, in about 1998 or 1999. And then finally, Mr. Horn at UCLA created the molten carbonate fuel cell. Now, there's always a joke that the two things that always puts people off about the molten carbonate is the name molten carbonate. But in fact, actually, it's a very clever fuel cell. And I'll go into this a bit more later, because all these fuel cell technologies are good technologies. There isn't a fuel cell that is a bad fuel cell. What there is misuse of fuel cells. The fuel cells have particular advantages in various technologies and various applications, and that we'll go into a little later. So next That's a good slide. Okay. The first applications of fuel cells, as I said, were in space, and they were used in the Apollo program. Mostly the Gemini program used them for a short period of time and then discontinued their use. But the Apollo program was the one that put the spacecraft on the moon, did the moon landing, and without the fuel cell, the moon landing would not have been possible. Buran, which was the Soviet spacecraft, also used fuel cells. Both used alkaline fuel cells, and in fact, the fuel cells made in Russia were very good. They were extremely good fuel cells. And I spent some time in Russia working with some of the people who actually came up with the fuel cells, and they were very clever chaps. They had an institute of electrochemistry in Novosibirsk that had 2,000 electrochemists. I don't think there are 2,000 electrochemists in all of Europe, and probably America as well. So they were very serious. In military applications, there is a lot of many fuel cells being used in military applications. The problem is we don't know a huge amount about it because they are military, and nobody wants us to know about what they do with them. But in particular, and this is what is interesting in terms of maritime, the particular use was in submarines. And they're used not only in submarines with conventional engines, but they're also used in submarines with nuclear engines. So they have a particular function, and that is that they run their backup systems, and they run the they use the hydrogen produced, for instance, in nuclear fission, and they use that to produce water. So it would be useful to know more about their use in submarines. All I can tell you is Ambrose Manikowski, who used to work for Martin Aircraft Company, did a lot of work on submarines, and used to say they were wonderful things, but they caught on fire. So that would be useful to know why they caught on fire. We've heard a lot about the use of fuel cells in automotive applications, starting with the Mercedes-Benz car back in the late 1990s. They are used now primarily in Japanese cars. Toyota's got involved in it, Honda, and a few others. The problem with using them in cars is two. One is cost, and the second is longevity. They will not become ubiquitous in cars like batteries do unless they are heavily subsidized. And that is part of one of the problems, the actual requirement for subsidy and the distortion of the market. They are used in Ballard buses. The first Ballard bus that I can remember was in Reykjavik. And the reason that Mercedes, who built the bus, put them in Reykjavik is that they wanted to stop any other person using Iceland as an example of a hydrogen economy. So they bribed them, in effect. And that brings me to one of the problems with fuel cell applications and fuel cell use, that is subsidies and ways in which the market is distorted and some quite dishonest applications. So we come to the other ubiquitous use, which is in stationary applications. And these are primarily for utility companies. The utility companies in the US had a splurge on fuel cells in the late 1990s. And you had companies like Los Angeles Water and Power and SMUD, which I've always liked, Sacramento Municipal Utility District. And they used proton exchange membrane fuel cells, but they couldn't afford the maintenance costs of them, so they were phased out in both cases. However, Doosan in Korea runs a very large power generating station of 170 odd megawatts, which use phosphoric acid fuel cells and PEMs and they have been doing successfully for some time, and they make phosphoric acid fuel cells, as does Fuji Electric in Japan. So there are still people making phosphoric acid fuel cells, and they were the backbone of the utility industries. I made a system for Black Country housing in the UK, which was the first application of fuel cells for domestic use, I believe, in Europe, but I could be wrong, but certainly in the UK. So next slide, please. So I told you about Doosan. The interesting thing about Doosan is that it is by far the largest installation, but not the only large installation. Larger installations were made, but the only one that I know that is running that is of that size is Doosan. The fuel cell buses, as we know, almost everybody's got a fuel cell bus. It's a sort of a matter of pride of most of the transport companies that they do have fuel cell buses, but they are expensive, and they have not solved the problem of fuels and the type of fuel. So most of them run on compressed hydrogen, which is rather expensive. I built the first 3 London taxis back in 1997 through 2000. And I decided it wasn't a terribly good idea. I'm not a great fan of using fuel cells in automobiles, if for no other reason than just the infrastructure doesn't exist. Although I also built the first hydrogen filling station in Hyde Park. If you go on the internet, you'll find that nothing of this exists anymore. But if you go on YouTube, if you go on YouTube, you will find pictures and bits of film of those first fuel cell taxis. Marine applications. There are some new marine applications. Surface ships, Hydra, for example, is a ferry boat built in Norway, or for Norwegian use. There have been others. They haven't been terribly successful. And one of the reasons, again, is their cost and the cost of operating them and the use of fuel. So there are real challenges. And the real challenges are capital cost and also operating costs as far as fuel is concerned. One of the more interesting areas is in data centers, where they have been used considerably. And Google, for example, has backup systems using fuel cells. And most critical applications like to use fuel cells because they're easy to operate and quick to start up. So how do we get around this, and how do we apply these to maritime applications? Well, the problem with that maritime applications is you need big, because ships are big. And so as a consequence, I'm working on completing work on a meter square alkaline electrode. And to give you an idea of what they look like, here's a small one. And here's a larger one. So we'll be able to build some very big ones soon, probably by the end of next year, the meter square electrode. That isn't where we will stop. There is a possibility we can go as far as 3 meters. The main issue regarding fuel cells of that size is heat management. And because of that, the alkaline fuel cell is particularly appropriate because it's got a liquid electrolyte. So therefore, heat management is rather simple. Well, I say that, but it's rather simple by comparison to other things. The next slide, please. So the other issue with fuel cells used in maritime applications is fuel. And one of the popular notions is the use of ammonia and direct ammonia fuel cells. I built direct ammonia fuel cells. They're not terribly efficient. And the real problem is that you end up with NOx. And NOx isn't good for anything other than being catalyzed. And if you catalyze them, it goes into CO2. And therefore, what you end up with is you end up with the thing you're trying to eliminate in the first place. So I'm not a great fan of ammonia. Also, the notion of producing hydrogen to mix with nitrogen and then to turn into a fuel that you can take hydrogen out of just seems to me not the cleverest use of hydrogen. Then there's methane. Methane can be converted into hydrogen by a system of water shift reaction, which is quite good. It means that you're increasing the amount of hydrogen by adding the hydrogen in water. But there are direct methane or methanol fuel cells. Direct methanol fuel cells have a problem in that they have a very short lifetime and they're not terribly efficient. So they do come with their problems, but they do have a use, and the use is that they have a liquid fuel, and so as a consequence, you can understand why they would like to be used. Hydrazine, I've explained to you already, is highly explosive, and I don't recommend you use it. Especially don't recommend you get it on your hands or breathe it in. It will kill you. But I'm not being overdramatic. Well, I am being a bit overdramatic. Then there is something that not a lot of people know about, which is aluminium. There is a huge amount of waste aluminium in the world that isn't recycled. But you can produce hydrogen by mixing aluminium with potassium hydroxide. And the interesting thing about this is it provides a byproduct, which is potassium aluminate, which is a commercial product and can be used for a variety of applications, particularly in the cement industry. But it produces quite good supplies of hydrogen, and I built a system for doing this just to test it, and it works very well. Finally, there's reformed biofuel. Now, this is the one that I like the most because A, it's cheap, B, it's very available. There's waste all over the world, and C, it actually develops other byproducts that have commercial value. And the reformed biofuel will produce hydrogen by going back to it, producing our friend methane. But that's not the only thing it produces. It can be short-circuited, and fatty acids can be used as a liquid fuel and reformed on board and on demand on ships. So it's very possible that this is the way things will go in the future. And I do hope so, because I think that the economics are unquestionably valuable. The next slide, please. So what do we need to do? Well, the first thing is fuel cells for ships have to be big. We're looking at 50 megawatts to 100 megawatts to meet the current requirements. It takes 3 kilowatts to move 1 ton of 3 kilowatt hours to move 1 ton of cargo for 1 nautical mile. So you can understand that in a ship of 50 to 100,000 tons, that you're going to need a huge amount of fuel cells. And that's why I'm developing this 1 square meter fuel cell to meet that actual requirement. Otherwise, what happens is we use fuel cells I showed you the smaller electrodes. Otherwise, we have to use the smaller electrodes, which means that there would be literally hundreds of thousands of fuel cells required in order to be able to shift a 50 to 100 ton ship. So this is why we need large fuel cell electrodes. In the same way as we use very large diesel engines, you can't imagine using a car engine and multiplying it God knows how many times in order to push a ship, nor a diesel engine to do that. You build very big ones. Now, you don't have gasoline engines running ships. You have diesel engines running ships, and they are enormous. The 1 square meter electrode is quite powerful. We can produce 7 kilowatts with just 1 electrode. So that gives you an idea of the dimension of the thing and the dimension that is required. As I say, ships require between 80 and 100 megawatts to push them through the water. And therefore, we require very large numbers of these, even the 1 square meter electrodes. So there is a dimension of going into the much larger size, 2 to 3 square meters at some point. However, everything is done by little steps, and those little steps start with, at the moment, the electrode size is about 20 centimeters by 20 centimeters. So getting up to the 1 square meter electrode is quite a step. So how do we get there? Well, first of all, the amount of fuel cells produced is relatively small. I built Europe's largest fuel cell factory in Cologne in the year 2000, and it produced maybe about 5 megawatts a year, but it was the largest. And things haven't changed that much since. There are a lot more fuel cells being produced, but in comparison to the size of the market, we need a lot more production of fuel cells. I mean, we need huge amounts of fuel cells being produced. We don't have that. The other thing is we need to be able to create the supply chains of materials, because again, the materials, for nickel, for instance, which is used a great deal in fuel cells, has not that many developers and producers. So we need to be able to ensure that we're able to use the materials and find the materials to be used in the production of fuel cells. Then there are catalysts such as platinum. We need to be able to not only find better ways of refining platinum, because that's the greatest cost of platinum. It's a misnomer that platinum is rare. It's not that rare. It's just difficult to refine. The problem then lies with the integration into vessels, and there is no real drive in this area. There's no real area of expertise. So we need to be able to bring about a seed change in the ability to be able to convert these technologies into marine applications. So we need marine engineers, and we need companies engineering companies that are capable of doing that. So we need a sea change in order to be able to provide this. And then finally, the cost of fuel cells at the moment, the cost of the 1 square meter fuel cell will be $800,000 per kilowatt. That really must come down to $400,000. And that can be done. That isn't outside the realms of possibility. Next slide. At the moment, there is no realistic funding, particularly in the UK. The amounts of funding for fuel cells is trivial by comparison to other nations. Germany is looking to build 5 gigawatts of fuel cells by the year 2030. They're putting 7 billion into hydrogen alone. Korea government is funding at 800 million per year, and they have been for a very long time. So they've understood that this is the way, this is a technology that requires significant amounts of funding, but even that kind of funding isn't sufficient. It must be even more. The USA also understands this. They have been putting more money into fuel cells, and you've got to remember that fuel cells were the biggest movers in the fuel cell area was the USA. So 750 million in the last budget is a good start, but there's a lot more to be done. So now I'm going to go into what fuel cells are, where they come from, and how they're made, and what types there are. The first type, the one that everybody knows of, is PEMs, and they are a membrane fuel cell, a solid membrane fuel cell, and they are acid. Acid has slower kinetics than alkaline, or in fact molten carbonate, well, alkaline as well. But it has they have two positive attributes. The first one is that because it's a membrane, it's relatively simple in terms of construction, but the materials are relatively expensive. Naphthalene, for instance, which is the fuel cell membrane, is an expensive material. And it has another problem, and that is that it's finicky. It requires hydration, and it requires a very, very minute balance of the materials that you're putting into it. So it's difficult to control. It is, however, small, and it is ubiquitous, and there are lots of people in the PEM business, and it would be good to see that enlarging. But it does have limitations, and it has limitations particularly in size. If you think that it is between 50 and 60% efficient, that means that the rest is all heat. Managing the heat is very difficult. Alkaline fuel cells are both membrane and liquid. The membrane suffers from the same issues that the PEM membrane does, and it is also expensive. So because it actually behaves in many of the ways that the PEM does, I don't think I'll spend much time on it. The liquid alkaline fuel cell has advantages and disadvantages. The disadvantage is that it's a caustic liquid, so therefore not great fun to use. I have been burned many times by potassium hydroxide, which is the actual main alkaline material used, or though sodium hydroxide can also be used. One of the things about liquid electrolytes, though, that makes them rather interesting is their conductivity. They have much greater conductivity than membranes. They're also easy to operate in terms of their temperature control. Solid oxide fuel cells is everybody's favorite fuel cell at the moment. It's been around for a very long time, as long as all the other fuel cells. It has some very good attributes. One is that it is internally reforming, and I'll go into that in a minute. But it's neither acid nor alkaline, so it gets out of that whole argument about which way the kinetics work. It's very clever. It's very efficient. It's got efficiency up to 85%. It doesn't require precious metals, so it has enormous advantages. So now what I'll do is I'll go through the fuel cell types. I spoke about the phosphoric acid fuel cell. They were very good fuel cells, and maybe they have a future. We don't know. Materials change, and as material technology improves, some of the notions that we had before change. So there is an advantage to going through this, to keeping an eye on phosphoric acid. The PEM, as I said, has naphthalene membranes. They're expensive. They're also terribly delicate. And in order to get the conductivity, they're made thinner and thinner and thinner. And the thinner they're made, the more delicate they become. Molten carbonate, very interesting fuel cell. Molten carbonate has huge longevity. You can keep one going for 10 years, even more, even longer. The problem with molten carbonate, however, is it's only applicable to stationary applications. It's very difficult to use for anything else because if you move it or transport it in any way, the molten carbonate solidifies through shock. This was found when they built a US destroyer using a molten carbonate fuel cell and it didn't get out of port. AFCs, as I say, uses potassium hydroxide. It's got huge advantages in terms of its efficiency and the amount of platinum you use in it. It's probably the smallest user of platinum. We use 5% loadings against 40% of loadings in other fuel cells. The SOFC, solid oxide fuel cell, uses zirconium on a steel plate, and that was very clever. But it does tend to come apart a bit. It's not terribly stable. And direct alcohol fuel cells, again, efficiency. And one of the problems with, for instance, with ethanol fuel cells is you can't crack the carbon, or nobody yet has been able to successfully crack the carbon compounds. I think I'm running out of time a bit, so I will move on a bit very quickly. The use of alkaline fuel cells in maritime applications is clear, and we would be remiss if we weren't looking into this in terms of being able to supply the kind of power required by large vessels. Small vessels can use any kind of fuel cell, but large vessels, when you get up to the 50 to 100,000 ton vessel, you need something big. And alkaline fuel cells are the ones that can actually provide that. So you're looking at a number of requirements for maritime applications. You need high efficiency because you need to be able to carry fuel that doesn't take up huge amounts of space. So you want to convert your fuel at the highest efficiency possible. You've got reduction of material costs. This is a notion that is quite difficult because we do use materials such as nylon, for instance, and nylon is tricky to fabricate. But we have to look at the actual cost of materials and the difficulty in manufacture. Manufacturing carbon plates, for instance, is a tricky and difficult application, and it also is not terribly convenient for maintenance. So you're looking for a fuel cell that is easy to maintain, easy to operate, is highly efficient, and where the cost comes down to something like $400 per kilowatt. And I think that's me done.
Yes, thank you, Nick. That was very interesting. So we are moving now to a more practical side of the things, how we're going to integrate the fuel cell into the maritime industry. So we're going to look at 3 areas: the economic implication, the market potential, and the route to the market. So as we know, the shipping industry is a significant consumer of energy because all the goods are transported, most of the goods are transported by sea, and we know that equivalent is of 1.9 billion tons of cargo each year. Meeting this demand requires around 5.7 billion kilowatts an hour of energy annually, which actually translates to an operating cost of 684 million per year at a rate of $0.12 per kilowatt hour. So this expenditure, combined with the pressure to reduce the emissions, makes it a most viable and a need to reduce. to find out a solution to the maritime. We are talking about the model of take or pay, which means that once a fuel cell is installed on a vessel, the ship operator is committed to utilize the assumed energy capacity regardless of actual usage. This provides a predictable cost structure while encouraging maximum energy efficiency on board. So how are we going to fuel this investment? Currently, the cost of hydrogen fuel cell it's around $800 per kilowatt or $800,000 per megawatt. As Nick mentioned also previously, as he was saying, we need to reduce this to half of it, which is $400,000 by the next 5 years. So how are we going to do that? Given that the industry will require an estimated 300 gigawatts of installed power to support its operation, this translates into a total investment of approximately $240 billion. So this is, going back to Nick's slide, the investment already from Germany, US, and Korea doesn't even add to this required amount. So how are we going to fund the conversion for the next 25 years? From our perspective, one of the most efficient is to utilize a 5-service agreement where capital expenditures are recovered at a rate of 0.18 pence per kilowatt, $0.018 per kilowatt hour. With a 100% return on investment over the initial 5-year period, the effective cost per kilowatt becomes $0.036. This cost structure not only covers the initial investment, but also ensures predictable returns. Furthermore, after the first 5 years, the fuel cells can be refurbished and extended for another 5 years, increasing their lifespan and enhancing the overall ROI. The ship operating requirement, Nick mentioned also briefly before in his slides, but I like to go through exactly what we need. So each ship will need an officer or engineer along with 3 trained technicians. These technicians must be trained in hydrogen fuel cell operations. Most of the ship systems are digitized and monitored remotely, which allows for very efficient and continuous onboard supervisions, which makes the cost more effective. In addition, we will need a dedicated waste-to-energy fueling facility to support these vessels. This infrastructure is very important because the vessel will come in the port and will need to align. For us, our route to market, we proceed in a few stages. We begin with an initial demonstration, which includes proof of concept, research, and training. This phase can vary in scale depending on project requirement and serves as a fundamental step for validating our technology. Once validated, we progress to a 5 megawatts shore-based system. This facility will act as a demonstration and training center for maritime operators and technicians, allowing for hands-on experience and system optimization. The final stage involves scaling up to 40 to 100 megawatt ship-based system, which will power a full-scale vessel. Throughout these stages, we require close collaborations with naval architects, shipbuilders, and compliance bodies to ensure compliance and operational safety. Throughout this process, I would like to clarify that CMS will act as a project manager, leveraging our exclusive license to deploy the technology within the maritime industry. While CMS doesn't manufacture the fuel cell, we coordinate with a consortium of specialized providers holding proprietary intellectual property to supply the technology. Our role is to bring the right partners, including naval architecture, shipbuilding, and compliance experts. Where we are now, we are currently at finalizing the 1 square meter electrode, as Nick mentioned earlier as well. Then we will be looking at development of waste to energy liquid fuel system, which will be designed to convert organic waste into clean hydrogen fuel cell. And with the support, we are hoping to launch by late 2025. To achieve our vision, what do we need? Which partners? And we're looking at three crucial. One is the investors. Without the financial backing, we cannot proceed. We need to fund development, testing, and scaling. Operational partners, which includes shipping companies and maritime service providers. They will be working on a day-to-day operations, maintenance, and compliance. And lastly, is the waste to energy partners, which usually are the local authorities, waste management companies. The companies will have access to waste resources. In this way, we can convert and create a circular energy system. And I think we are at the end now. So I'm passing over to Jake for the Q&A session.
Brilliant. Thank you both for a great presentation. Let's love about both sides. So open the panel. We do have a Slido going for questions. So if you do have a question, please do add it to that Slido Q&A section and we can get that answered. While waiting for some more, there are some existing ones in there. So I'll just pull some of them out. So we've got a question here saying, why has it taken so long for maritime fuel cells to be adopted? Why don't we see them in use already? Maybe that's one for Nicholas.
Well, it hasn't in essence because they've been used in submarines for a very long time. The reason being, I suspect, is because of cost. Diesel engines are very efficient and they're very economically efficient at the moment. We've got to be able to bring the fuel cell technology up to the same kind of characteristic, or in fact, actually to be competitive, to be better than diesel engines in the sense of their costs and their operational capabilities. That's the reason why it hasn't. There's also, I've got to say that governments, by and large, are not very good in the fuel cell sector. They are protective. They're protective of various types of technology. They are protective of the status quo. So we don't get a huge amount of support from government. There's almost no support in the UK, for instance. So this is the reason why we haven't seen more maritime applications. We should. There's no reason why we can't. And certainly the technology is available. Even the technology, this kind of technology is available now. So the answer is, I think it's a political issue as much as anything else.
Okay, thank you. I've got another question online asking, do you think that fuel cells alone will be enough to transition, or do you think there'll be a combination of different alternative fuel solutions?
I think that the nuclear option is very interesting, and I think the future lies in both fuel cells and nuclear. And the interesting thing is that fuel cells and nuclear work well together. I'm not convinced that hybrid of any other particular type other than batteries, but that batteries do make some sense in terms of hybrid fuel cell technology. Outside that, there could be a transition where fuel cells are used as part of propulsion systems for particular purposes. That would be a good entry. But I don't see that there are any combinations of combustion technology, for instance, with fuel cell technology.
Thank you. Isabela, do you have a view on this as well?
Well, there are so many technologies coming into the market and many discussions. Um, I feel sometimes there is the topic of of the year. Like 4 years ago, during the pandemic, nobody would talk about hydrogen. I'm talking purely about the maritime sector. The last 2 years, everybody, hydrogen is number one. Ammonia became a topic recently, but now I can see how the maritime industry is finding ammonia not so interesting or not number one anymore. So I think for me personally, I've shared Nick's idea. I believe that the same, the fuel cell and the nuclear is added to future fuels of the future. But it will be interesting to see how the shipping industry will adapt to this, and we need funding. I think this is the main issue that all the new technology have, and there's not enough funding around. And it was really interesting on Nick's slide on how much Germany has invested compared to UK, for example. And from for the last 5 years, I can see many companies going abroad for investment. So I really wish to see changes coming up with the new government in the UK and remain positive that we'll see that.
Great, thank you. We've got more questions coming in. We've got one from Robert Fenton asking about cold ironing applications. So talking about power from shore.
Well, I actually wrote a report on cold ironing for using fuel cells as a method for cold ironing in Liverpool, and the notion was to build a barge which could take waste, convert waste into hydrogen, and put it through fuel cells to be applied to ships, whereby you would not take up dock space, which is one thing. And then the second thing is you could offload waste from ships. But I will say that the amount of waste coming off ships would be minute in terms of being able to change it into hydrogen. However, having said that, outside in municipal areas, they've got huge waste problems, and this would be a way of supplying hydrogen by the use of their municipal solid waste. It's practical, and it's not that terribly expensive. So we could do that, and we could produce certainly a barge that would produce, say, 20 megawatts, which would be more than enough for ships. And it would be very flexible because it could be used to push around. Now, there are a number of people who have tried this. The US has tried it, but again, they use the wrong technology. The Netherlands is looking to this system as well, but again, it's the use of the technology. You use the right technology for the right applications, and what you don't do is follow technology that is politically correct. You follow technology that is economically and scientifically correct, and unfortunately, that's not what happens at the moment.
Cool, thank you. Got a probably final comment, conscious of time. So we've got a question from John Key asking, yeah, thank you for a great presentation. Are there any particular vessel types or use cases within marine that are particularly well suited to fuel cells, i.e. point-to-point ferries and short sea journeys?
The answer is yes. The most applicable vessels, believe it or not, are military, because you have a very low heat signature in terms of low temperature fuel cells, and they're quite easy to fuel. Point to point, fuel cells, hybrid systems using fuel cells and batteries are appropriate because you have time in which to charge the batteries while the ships are disembarking and embarking. So there are applications within the framework of existing technologies. So those ships may be the first types of ships to be used, but again, the problem comes down to you need something big, because a ferry is a fairly big ship and does require quite a lot of power. So you still have got to use very large systems, and it's the large systems that are required to be built. The as I said, the military ships are a very good way to start out, because they do need these kinds of technologies. But we are mostly interested in large cargo vessels, and it's the large cargo vessels that are producing most of the CO2, most of the greenhouse gases.
Great, thank you. We do have two last questions, so I wonder if we could do some short, quick answers to them. So one asking, does the fuel cell production process have any negative environmental impacts? Nick, you're probably the expert on this. Have you got your workshop behind you?
Yeah, only. No, not really. Most of the components are 3D printed, so you have recycled materials. You're using recycled materials as often as not. The other materials you're using are carbon, which arguably might have some localized issues, but not really. There aren't, by comparison to diesel engines and all the other engines, the amount of environmental impact is trivial.
Yeah, I think, yeah, just reinforcing that it's important to take the whole life cycle impact. But yeah, thank you for that honest answer. And then final question from Martin online raising, could a hybrid solution combining multiple options, including heat pumps, fuel cells, renewable energy sources, all working together, work for communities as well?
Yes, you could do that. I will say Stirling engines, very interesting, because you're producing heat as a byproduct from the fuel cells. So therefore, Stirling engines make a lot of sense, even though they're only 40% efficient. If you're shaving the efficiency, Stirling engines could be quite useful.
Brilliant. Wow, thank you very much, everyone, again for joining this first in the series of workshops for Maritime UK webinars. Brilliant, thank you all. Please do sign up for our next one, which will be held on the 9th of December, and QR code for that one now on the screen. Thank you again to our wonderful speakers. And if you do have any questions that we weren't able to answer, then contact details for Isabella on the screen there. Thank you very much again, and see you in a couple of months for the next one.
Bye.